Last lesson today. Very exciting. So we are going to use the trig identity that I touched on in the last clip, this angle sum identity, to prove other identities. So one thing that I want you to recognize about math in general is the way that, if we have one theorem, say we have theorem A leads us to theorem B, right? Theorem B lets us prove theorem C, right? From C we get to D, right? So we get this chain of laws or rules or theorems. So from this angle sum formula, we can derive what's known as the double angle formula. Okay, so 2 theta is, of course, theta plus theta. All right, so if we were to plug in to this identity, so I'll do the first one for you. So this would be my A, and this would be my B, right? So A and B are obviously equal in this case. So if I plug in using this formula, I would get sine A, so sine theta, plus times cosine theta. And then over here, I would get cosine theta times sine theta. Well, I have a commutative property that tells me that I could switch the order of my multiplication, right? So then what I would have is sine theta times cosine theta twice, right? So this would be equivalent to 2 sine theta cosine theta. Right? And so this becomes one of my formulas. This is known as the double angle formula for sine. Okay, so that means as I'm doing some of my exercises later, anywhere that I see sine 2 theta, I'm going to replace that with this expression. Right? So you try cosine 2 theta. Right? Plug in theta over here. Plug in theta for both A and B. And see what you get. All right, so pause the video and try it. So you should have recognized that, oh, I should have my theta. You should have recognized that you had cosine theta times cosine theta, so cosine squared theta, minus sine squared theta. That means that anywhere later in the exercises, anywhere that you see a cosine 2 theta, right? Anytime you see this expression, you can replace it with its equal. Now, there's other ways of rewriting this expression. So as I mentioned in the last video clips, in trig, there are many, many ways to write the same equivalent expression. So what I can do is I can use the fact that cosine theta is equal to 1 minus sine squared theta. So I can take this expression here in blue. I can replace cosine squared theta with its equal, which is 1 minus sine squared theta. Right, so I'm putting that in place of cosine squared theta up in that expression in blue up above, and I would get this right? So this would also be equivalent to cosine of 2 theta because I took its equal and I replaced something with its equal with another term's equal. Right? So I've said many times before, if you want to be a good mathematician, you just have to substitute things for their equal. All right, so this is another way that I could write cosine 2 theta. So that's going to make working with this more challenging because you're going to have to choose what would be the best substitution for the problem at hand. You see cosine 2 theta, you can replace it with cosine squared minus sine squared theta, or you could replace it with 1 minus 2 sine squared theta, or we can use the other fact then that sine squared theta, right? What could we replace sine squared theta with? Right? I could replace sine squared theta with 1 minus cosine squared theta. All right, so pause the video, come over to sine squared theta, and replace it with its equal. Okay, when you did that, you should have gotten, when I distribute my negative, now this becomes minus minus, which becomes plus plus, right? So I'd have cosine squared theta plus cosine squared theta when I distribute that negative. So that's 2 cosine squared theta, and then minus 1. Right, so I have 3 different equivalent ways that I can write the identity cosine 2 theta. Now, this thing number 3, this is something that you will use in Calc 2. If you don't go to Calc 2, you'll probably never see this again. But if I wanted to, say, rewrite cosine squared theta, right? So I know that cosine 2 theta is equal to 2 cosine squared theta. If I want to, then I can solve for cosine squared theta. All right, so what does that look like? That would look like adding a 1 on both sides, right? Add a 1 to both sides. I'd get this alone, and then I'd be dividing both sides by 2 after I add the 1 to both sides to isolate the cosine squared theta. Okay, and I can rewrite cosine squared theta as 1 plus cosine 2 theta over 2. So you go ahead and verify that if you solve this identity for sine squared, that you would get this. Okay, so again, I didn't even assign you any exercises with this today. If you go and take Calc 2, you will use this. You'll actually use it quite a bit in Calc 2. So on to the last page. We're just going to practice a little bit using these double angle identities. So you'll notice that there are lots of trig identities on that handout that I haven't even touched on. I haven't even done examples on. We could spend weeks on trig identities. But for those of you that are just taking Calc 1, you should be fine with the little bit of work that I've done with the trig identities. Probably in Calc 1, honestly, I'd be almost even surprised if this came up much in Calc 1 again. In Calc 2, it comes up a lot. But if you can do the basics, right, and you know your sine squared plus cosine squared equals 1, and you know all your reciprocal identities, that should be enough to get you through Calc 1. But anyway, let's go on. So just after I tell you you don't really need to know this for Calc 1, we'll practice it anyways. Okay, but again, using sine, I've got sine 2 theta, right? That means I need to substitute for its equal. Okay, so anywhere I see sine 2 theta, I put in 2 sine theta cos theta. Okay, so I replace that with its equal. Then I get the plus cosine theta and theta net x. And then in the denominator, I have cosine squared. Okay, so looking at this numerator, all right, so remember in the denominator, cosine squared is cosine times cosine. Okay. In the numerator, I could factor out a cosine. Right, both terms have a cosine. If I factor out a cosine, I would be left with 2 sine. Don't forget the plus 1. Sometimes students, they take they factor something out and they forget to write +1. Because remember, I need to be able to multiply this back in and get back to what I started with. All right, so we know we can't cancel out of a sum, but we can cancel a factor when there's a product, right? So I've got this cosine theta. I could cancel that out with one of these cosine thetas, and I could simplify this down to 2 sine theta plus 1 over cosine. If I wanted to, if that wasn't one of my choices on a multiple choice, I could, nah, I'm gonna leave it like that. Well, no, let me just show you this. I could go like this. I could divide each one by sine, or I'm sorry, each one by cosine. I could go like that, right? I pulled the 2 out in front, and then I could do 1 over cosine, so I divided each term by cosine. And this, sine over cosine is tan, so 2 times tan, and 1 over cosine is cosecant. Right? That's part of why on the homework I pretty much exclusively gave you multiple choice, and I'll do that on the final exam as well, because otherwise you would say, well, how do I know which answer do you want, right? And so again, we've got this trig expression where this doesn't look anything like this, but these two are equal, and neither of these look anything like this, and yet all 3 of these expressions are equal. All right, so we especially see this in trig. Things do not have to look at all the same to be the same. All right, so let's do our very last example. So I've got cosine of 2x, so I need to use one of the double angle formulas. And this is where, now I have x instead of theta, but that's okay because, you know, x is just representing the angle, so it doesn't matter if I call it theta or x or beta or alpha. My choice of variable is irrelevant as long as I'm consistent, right? I have to have all x's in one problem, all thetas within the other problem. I have to be consistent about what I call the variable. But my choice of representing the angle doesn't really matter when it comes to using the identities. So I have to pick, all right? And so you might have to, on your homework, it might take just a little bit of trial and error. You might try one identity, not get anywhere. The reason I think it would be best to use this first identity is notice cosine squared minus sine squared. That's the difference of 2 perfect squares, right? Like if I had a squared minus b squared, difference of 2 perfect squares, I could factor that into a plus b, a minus b. Okay, so this expression, cosine squared minus sine squared, that if I happen to pick that identity, I could plug in exactly as is, or I could look at that in factored form. Because what I'm doing is I'm paying attention to what's in my denominator. Right? So I would have cosine squared, and you know what? Text box. So in the numerator, I would have cosine x minus sine x times cosine x plus sine x. Right? And then, of course, notice what I have in the denominator. Okay. I have the sine first instead of the cosine, but that, you know, I have a commutative property of addition that tells me if I want to change the order of the addition, I can. And then when I do that, I can see that this factor here cancels with what I have in the denominator, and I have a final answer of cosine x minus sine x. And we're done.